So thank you very much. Let me start by thanking the organizers for giving me this opportunity to speak here. It's a very nice place. It's a bit colder than I expected, but beautiful. So I would like to summarize a series of works we have done in investigating this resurgence ideas, resurgence structures and transseries in integrable models. In particular, we calculated the ground state energy densities, and then we discovered very nice structures. So I will summarize a series of papers, and the papers in the bottom line, they are more experimental and numerical. When we try to figure out the resurgence structure, and later in these last two papers, we actually provided the complete and full analytic transseries for these problems. So let me start by stating the mathematical problem. Maybe for a mathematician, a number theorist, uh, I can just state, Jens, for you that we have this linear integral equation. So we would like to solve that linear integral equation, when the right-hand side, the source term, this cosine hyperbolic alpha theta, and typically in the applications we have alpha equals 1 or 0, but we generalize this problem a bit. And this kernel will be related some logarithmic derivative of some scattering matrix, but in general could be any kernel which is of a difference form. And we would like to solve this linear integral equation. And then why is it non-trivial? It's non-trivial because we are integrating only on an interval. So our function is non-trivial only on an interval. Outside, this chi function is 0. If this whole equation were defined on the whole line, we could just do Fourier transform and solve the problem. But this is on the interval, so the solution is not so simple. But nevertheless, we will make a systematic solution around the b going to infinite limit. So that's the limit when we can easily solve. And we will calculate observables. The observables will be related the Fourier transform of that unknown function. They are the generalized moments integrated on this interval minus b and b. And we will be interested in that observable as a function of this b. And we will do resurgence. So what is the small coupling? The small coupling is 1 over b. So when we do perturbative expansion, perturbative series will be an expansion in 1 over b, but we will see non-perturbative corrections. And the non-perturbative corrections will be organized in this e to the minus b. We also will have some log b terms, but they can be resummed by introducing a better coupling constant. So what I will provide at the end of the talk, I will provide the complete transseries solution for that observables. So this is a perturbative expansion in 1 over b, and the non-perturbative expansion in e to the minus b. The n equals 0 term is the perturbative expansion, and those are all the others, the non-perturbative terms. And we will ask questions whether, for example, the perturbative guys, this E0n coefficient, determine all the other non-perturbative corrections or not. A is just this A. This is how I denoted this perturbative coefficient. This capital A. Capital A, it's like an instant on action. And here A will be 2. Yeah, sorry. It depends a bit on the model, but in the O4 model, I will analyze a lot. Capital A is 2. Yeah. So that's the question we will ask. And now I would like to try to motivate why we analyze this linear integral equation. So the first motivation comes from quantum field theory. So the very same equation appears in the analysis of the ON nonlinear sigma models and also other 1+1 dimensional integrable quantum field theories. So I will do resurgence in the quantum field theory. So this quantum field theory lives in 1+1 dimensions. It has n fields which are restricted to live on the sphere here. The action would be just the free action, this first term here, with that constraint that they are living on the sphere. But to give some non-trivial dynamics, we will couple this whole theory to a magnetic field or an external field. So this theory has an ON symmetry. I can make rotations in the sphere. And I can just pick up one of these conserved charges, say the rotation in the 1-2 plane. I take that conserved charge, and I couple that charge to this magnetic field. And I formulate the Lagrangian in such a way that if I would do a Legendre transform and would calculate the Hamiltonian, that at the level of the Hamiltonian, I have the free Hamiltonian minus this charge, this conserved charge in the 1-2 plane times the Hamiltonian, so times the magnetic field. So I will shift the Hamiltonian by this conserved charge. So that's why I'm just explaining why I have this h square term here, and I will do the calculation in Euclidean. So this is the theory we would like to solve, and what we would like to calculate, we would like to calculate the free energy density in this quantum field theory, and we would like to do it in perturbation theory. So introducing this magnetic field on this 1-2 plane, then the vacuum will be when the first field has a value 1, and I start to analyze small fluctuations around this ground state. So I'm saying the fluctuations are so small in terms of this bare coupling lambda square, so it's proportional to lambda square, and I have n-1 fields, and I just formulate the path integral for this n-1 field, and I would like to calculate the free energy density. I'm emphasizing this so there is a Lagrangian behind, and then you can do the usual Lagrangian perturbation theory. Of course, you have ultraviolet divergence, you have to use dimension regularization, and then you will make eventually a perturbative expansion. Sometimes to connect with an integrable description, it's better to analyze not the free energy density, but instead the density, which is, and the ground state energy, and they are related to each other as Legendre transform. So this is the setting. You could do calculations, and then even I show that you can actually do calculations. This is quite general for the ON theory what I'm explaining now. But in the ADS-CFT correspondence, some early days, the O6 model appears. When strings moves on S5, then it's described the O6 model. And there were some proposal for a physical quantity in this O6 model in 2 different ways, and then they didn't agree. So then at that time, Grisha Korczemski approached us with my friend János Balogh, who was an expert in this subject, and he asked if we could calculate actually the free energy 1 order higher than it was available in the literature. So we did this 2-loop field theory calculation, and then indeed you just do the calculation in terms of the bare coupling, you renormalize the coupling, you calculate how you're at a given scale, and then you see how the coupling is running, and then you will see that there is a dynamically generated scale, and you can introduce a running coupling in terms of this dynamically generated scale and the magnetic field. So it's like lambda ms bar, and then you can express the free energy density in terms of this running coupling. So this is a real field theory calculation is behind. It's very tedious, actually, even to go higher order. So we calculated only up to that order, but it was enough at that time to decide which proposal was correct. I also mentioning that after the Legendre transform, you can express the ground state energy perturbatively in terms of another running coupling. And these running couplings are nice in the sense that they resum all logarithmic and log h, the magnetic field, and then all higher logarithms. So eventually both the free energy density and the ground state energy can be obtained as a power series in this running coupling. This is a very tedious calculation, and ideally it would be nice to calculate many terms perturbatively, but it's impossible. But the point what I would like to make that in principle this is a well-defined problem. If you sit down, you just analyze the Feynman diagrams, you do the calculation, then you could calculate many terms. Why we like this particular model, this ON model, that it's a quantum field theory, but it's integrable. So I can calculate many perturbative terms, not in that language, but in the integrable language. So I will switch that language now. So I'm explaining now that the linear integral equation I will analyze actually appears in statistical physical system. So it appears many places, so that's why we like this linear integral equation. And the other place where it appears, which I'm explaining now. So imagine we are in 1+1 dimensions, and we have an integrable model with particles which scatter on each other with just one particle type. We put many particles on the circle, and we would like to analyze the energy spectrum of this system. So we have some dispersion relation, the momentum of the particle depending whether it's a relativistic theory or non-relativistic theory. If it's a relativistic theory, the momentum is just m times sinh theta, theta is the rapidity. If it's a non-relativistic system, then it's just the velocity m times theta. And I would like to calculate the spectrum, and to calculate the spectrum of this integrable model in a finite volume, you have to demand momentum quantization. So you have a multi-particle state, it's an integrable system, they scatter, the number of particles stays the same. Momentum quantization means if you just pick up one particle and you move around the volume, then the wave function should be single valued. So it means if there were no scattering, you would pick up just the phase, e to the I pjl, and this should be 1. But there is a scattering between these particles, so when you move around, you pick up the scattering phase of all the other particles. So the momentum quantization means that this product, together with e to the pj, should be 1. We would like to solve that equation in the thermodynamic limit. So we would like to put a lot of particles. And in calculating the thermodynamic limit, one more. So what we do, so we have this finite circle and we start to put particles. And they are fermions. And I just have seen a very nice sign which is explained. This is a very nice historic site, and actually Fermi was here formulating how fermions behave. And then these particles in the integrable models, they are either fermions, or if they are bosons, then the scattering matrix at 0 rapidity is -1. So they behave like fermions. So you cannot really occupy the same state twice. So in this finite volume, you start to put particles, they start to occupy small momenta, but then when you put more, they will occupy, I'm showing here, some interval, Fermi C, between -b and b, they will start to occupy that momentum states. And then we are sending the volume to infinity, the number of particles to infinity. In this thermodynamic limit, the ground state will be described by this chi theta rapidity density. And this rapidity density, you can calculate just taking the thermodynamic limit of that so-called beta ansatz equation. So the thermodynamic limit of the beta ansatz equation, if you take logarithm and differentiate it, it will be exactly the linear integral equation I started my talk for the ground state energy. So this linear integral equation, when you integrate between the Fermi sea, the rapidity density with the kernel, which is the logarithmic derivative of the scattering matrix, this is a linear integral equation. On the right-hand side, you have the derivative of the dispersion relation, the derivative of the momenta. So if you can solve this linear integral equation, then you can calculate the density of the particles and you can calculate the energy density as a function of this B of the Fermi surface. So this problem appears, for example, in the Lieb-Liniger model, the Godin-Young model, in many, many integrable statistical physics models when you have only one particles. In quantum field theories, typically we have more than one particle. Like in the ON models, in the previous model, if I quantize it, I will have a vector multiplet of particles, and when they scatter on each other, it's a non-diagonal big scattering matrix. But what the magnetic field will do, because the magnetic field couples to this charge, so on this vector multiplet, only two particles will be charged. And one of them will have a positive, the other is negative charge. So you introduce a magnetic field, then you can somehow arrange so that only one type of particle condenses in the vacuum. And this previous analysis I just explained to calculate the ground state energy can be applied also for the ON model. So in the ON model, you can calculate the scattering of this only particle which condenses in the vacuum, and this has this very non-trivial form. You see, this is the scattering of this very single particle which condenses in the vacuum. So taking the logarithmic derivative, this is going to be the kernel with which we would like to solve this linear integral equation. Yes, Andrea? Yes. So what I do, I take the beta ansatz equation, I take the logarithm, and I assume that in the thermodynamic limit, there is a density of particles. And usually in the thermodynamic beta ansatz, you have the density of particles and you have the density of holes. But here I'm at 0 temperature, so I have no holes. In the vacuum, I completely fill, the ground state completely fills. And then I'm taking the logarithm and then just differentiating that beta ansatz equation, I got this linear integral equation here. Yeah. So this is the equation I would like to solve today. So this is going to be the complete solution of the ground state energy in the Lieb-Liniger model, and also in this ON model in a magnetic field. Yes. Next slide. Yeah. So again, today I would like to talk these linear integral equations. I generalize a bit because you see I will add this alpha. It will be slightly more general. Alpha equals 1 is the previous case. So let's do it for generic alpha. And the observable, previously we encountered the observables for beta equals 0 and beta equals 1, but why not generalize it? So what can this integral equation describe? So I just mentioned that in this two-dimensional integrable quantum field theories, I can introduce a magnetic field coupled to a conserved charge, and I can push the particles such a way that only one type of particle condenses. Then I'm in this situation. For example, I explained for the ON models. But there are many other models. There is the n equals 1 supersymmetric extension, the ON sigma models. There is the ON Grosvenor models, the SUN chiral Grosvenor models, the SUN principal chiral field, they are all integrable models, they all scatter non-diagonally, but introducing the magnetic field, it's exactly the same equation. The kernel will be different. The kernel will always be the logarithmic derivative of the scattering matrix. Yes. Yes, yes. You mean the thermodynamic limit? Yeah, it's never really proven. It's never really proven. We are not mathematicians, so. So what is non-trivial? In a Lieb-Liniger or a Godin-Young model, when you are a quantum mechanical system, then this finite size spectrum, when you take a particle, move around, and quantize the momenta, it's exact. But these are quantum field theories. And quantum field theories, you have vacuum polarization effects. The vacuum is not trivial. So you have some exponentially small correction in the volume, um, so this beta ansatz equation I showed, they are valid up to exponential small correction. And if you have a few particles, still this is a good approximation. But I'm talking about thermodynamic limit and finite density, and they somehow start to overlap. So it's not clear whether this limit is correct. But somehow what happens that if you go to very, very large volume and they are separated, then this limit exists. And then when you start to shrink a bit the volume, say, then there is no phase transition. So you can analytically reach this other domain. But there is no proof, but there are indications that the limit exists, and then it's described by this linear integral equation. Yes? Yeah, there is, yeah. Yeah, that is a unique solution. Yeah, I will use it because I define a quantum field theory and I will make a perturbative expansion, and then usually you do not really have a control about the non-perturbative effects. How do you know which non-perturbative corrections to add? But here you have this linear integral equation and you can solve numerically. So you have a you have a well-defined answer. So it's a very good framework actually to test all these resurgence ideas because there is a unique answer. Yeah. So I would like to also mention that one of these ON models, the O3 model, the kernel simplifies a lot, and it's a rational kernel. So the kernel is just 1 over theta squared plus pi square. It's rational, and then this is the very same kernel what appears in the Lieb-Liniger model and also the Godin-Young model, which is a theory of fermions. Even more, the very same kernel appears in the love equation, yes, as you were interested in. So if you analyze it's a very old classical problem in electrodynamics. Let's assume you would like to calculate the capacity of this coaxial disk capacitor. So think of two disks, they are a distance d, and then you would like to calculate the capacity. And then what you will find, you will exactly get the same integral equation here. This is love equation with that kernel. And the observable you are on the right-hand side is alpha equals 0. And the observable you are interested in, the capacity is just this O00. So I will also calculate that guy today. So this equation appears in many, many places. So hopefully I can motivate you why we analyze it. First, I would like to show how to expand perturbatively this integral equation. This is already very non-trivial. How to get the perturbative coefficient. And then we will play a game. So we will calculate many of these perturbative coefficients and analyze the asymptotic behavior. And this is how we will learn about the analytic structure on the Borel plane. I will just extract from the asymptotics. And then we will see, because we have a numerical solution of the problem, we will see how we could get the same unique, well-defined result from the asymptotic analysis and Borel resummations. And then we will ask the question whether the perturbative part actually determines all non-perturbative corrections. And the O4 model, they determine all of them, but in the O3 model, they don't. And O3 model is very special because it has instantons. All the other ON models, they don't have instantons. So it seems somehow the instantons are not captured by the asymptotics of the perturbative guys. Then I will present the full solution based on the Wiener-Hopf method, and I will conclude. Wow, yeah, that's just. To expand this, this linear integral equation, maybe let's just flash again. So this is the linear integral equation. I would like to expand around b going to infinity, where I can solve in Fourier space. So there is this Wiener-Hopf method, but it's actually very complicated and painful. So when we, for the O6 model, we were asked to calculate the second order correction, then it was simpler to expand. It was simpler to do the calculation in field theory than to expand this linear integral equation to second order. So it was so complicated until Dima Volin came out a very nice idea, how you can calculate many, many terms. And his idea was that instead of looking at this linear integral equation and the rapidity density chi, so why don't we analyze its resolvent? So he introduced the resolvent of the problem, which was defined in this way. The resolvent is an analytic function everywhere except a cut between minus b and b. And the jump on the cut of the resolvent is the unknown chi function we would like to calculate. So that's the definition. Once we know the resolvent and then say we analyze how it behaves large theta, then we see that that expression will provide us the density. It's also good to make a Laplace transform of the resolvent. The Laplace transform of the resolvent will contain information of what is generalized observables. In particular, the energy density can be obtained at a particular point on the resolvent. Now the idea, he had this idea how to make a 1 over b expansion was that, so let me just put all of it, yeah. So we have this resolvent and the chi function, and the chi function lives between minus b and b, and then we know there is a cut. And he could manage to parameterize the resolvent with this cut between b and minus b in coordinate theta space with this ansatz. So this ansatz is an O4 specific ansatz. For other ON models, the form is a bit more complicated because you also have logarithms in the cuts. So you could have some log theta minus b divided by theta plus b to some power. In the O4 model, the ansatz is very simple. So you have the square root of theta square minus b square. So he made an ansatz for the resolvent, which is valid in around 0. And using the Wiener-Hopf solution, one can easily make a parametrization and assumption for the resolvent in the Laplace place. So there are two parametrization of these functions. And by matching these two in a common domain, he could derive algebraic equation relating this C coefficient with this Q coefficients. So it's two different. You parameterize your function from the Wiener-Hopf method near the edge, how it behaves near B. This is one side. On the other hand, you parameterize because it has a cut, how it should look like. And then in the common domain, you just match the two parameterization. And this provides algebraic equation which relates the C and Q coefficient and completely determines them. So that was his idea. And if you do the calculation, then it was really painful to do it in the field theory. And we have this linear integration, but it's still very difficult. But using his idea, you can easily calculate in Mathematica, he calculated himself 22 coefficients. And then later it was extended by Marcos Marino and Thomas Reis, and they calculated 44, and then we calculated 50 coefficients. So imagine you have 50 coefficients analytically. How do they look like? So they look like that they contain this small a, what I denoted, this is log 2. So they have log 2 and they have odd zeta functions. And then you should imagine if you calculate 20, 30, and then you have all possible, everything can appear at a given transcendentality orders. At a given order, everything appears up to that transcendentality. So these expressions are growing and they are very, very large, but you know them exactly. So what can you learn from it? So that's first of all, it's very nice to have a quantum field theory when, although you cannot do perturbative calculations, but if you could, you would get the same result, up to 50 order. So and then you can also switch from, here we did the calculation in 1 over b, but you can somehow switch to the running coupling, and then you can calculate the free energy density. Similarly, we would calculate from field theory in the running coupling, and what happens that this log 2 disappears, and you have these odd zeta functions. So you have many, many, many terms. You know them analytically, but somehow this 50 is still not really enough to analyze the asymptotical behavior, and this is what we would like to do. So what we did instead, we said, okay, don't do the calculation analytically. Let's try to solve these algebraic equations numerically with very high precision. Yeah, one more point. So this whole analysis was started by this company, Peter Hasenfratz and Ferenc Niedermayer and Maggiore. And the reason they did this analysis on the field theory side and this integrable model, ON scattering integrable model, and introducing the magnetic field, because they wanted to relate the dynamically generated scale lambda to the mass of the particles. So this is it's a very famous problem. If you could do the same thing in QCD, you would get this $1 million prize. Yes, so by doing the calculation on the field theory, they got the expansion of the free energy perturbatively in h over lambda, the dynamically generated scale. In the other hand, when we expand in the integrable scattering theory, then the result comes in the ratio h over m. Comparing these two perturbative expansion, they could relate the mass of the particles to the dynamically generated scale. And the result is written here for generic ON models. So this was very nice, and it was a nice conceptual motivation to do this calculation, but now we would like to do it better. We would like to calculate many terms and then see these resurgence properties. So what we did, so we calculated really many perturbative coefficients, 2,000 perturbative coefficients and 7,000 digits. And we did it for the density, for the energy density, and for the free energy. And we started to play a numerical game now. You have that many perturbative coefficients, so let's see how they grow. That's the game. So you have the perturbative coefficient, and you will see they grow like factorial. So maybe, Jens, this is another example when you can go beyond the example I already told you. So you have some perturbative coefficient, you grow factorial. So you divide by this factorial grow, and then there is some constant piece, there is an alternating piece, but also there are 1 over n corrections. And then you can extract all these numbers very precisely. You can use this Richardson transform. So using the Richardson transform, you can kill the 1 over n corrections, and then you can extract this constant piece, the alternating piece, with very, very many digits. So yes, so that we did, and we extracted this number, and I will come back to this point. Just I would like to give a motivation why we go to the Borel plane. We go to the Borel plane because we are calculating something in the path integral, and then you can think of switching to the Borel plane like performing the path integral in two steps. First, you fix the value of the action, you do the path integral for that action, and then you do this extra integral for the action, for all possible actions. So this is basically the Borel transform. So it's very natural in field theory how the Borel transform appears, because this is just performing the path integral in 2 steps. So we go to the Borel plane, we have this factorially growing coefficients, we divide by the factorial, and then it's a well-defined function with a finite convergence radius, and if we divide by this 2 to the n, then the convergence radius will be 1. We have so many terms, we could make easily a Padilla approximant, and then this is, I'm showing you the Padilla approximant of our function, and you see it's obviously there is a pole at 1, there is a cut starting at -1 from the alternating part, and we could see easily that there is a cut starting at 2. So from like 1,000, 2,000 coefficient, you can easily see this picture. And then you ask, okay, so this is the Borel plane, but how can I get back the physical quantity, which I could calculate by just integrating numerically the integral equation. And then we already heard talks about that. We would like to make some, of course, singularities on the real line. So we would like to shift the integral a bit above or below. Shifting a bit above, then of course there is an ambiguity how we shift. But we can shift a bit above, you perform the integral, and then we will see that they will have imaginary parts, so it's not really the physical answer. And but the magnitude of these ambiguities and imaginary parts will be exponentially small. So what we did now, we just we use the sophisticated way, sort of. You have to make an analytical continuation of your function in order to perform this lateral Borel resummation, and then we use the conformal mapping, for example, to get an analytic continuation of the function such that we could precisely integrate a bit above the real line. And this result, what we got from like 2,000 coefficient, we compared with the numerical solution of this TBA equation. So we solved the TBA using the Chebyshev method. We could calculate the solution, so it's a unique solution, and we could easily calculate 30 digits precision in the O4 model. So that's the physical result. On the other hand, we had this asymptotics of the perturbative coefficient. We went to the Borel plane. We made an analytic continuation by the conformal mapping, and we integrated a bit above the real line. And we found that there was an imaginary part. Of course, solving the TBA, there is no imaginary part, it's a real solution. And we could fit this coefficient, the behavior of the imaginary part. There was an exponentially single e to the -2 over alpha non-perturbative piece, and there were higher corrections, and these higher corrections had a series expansion, and we numerically fitted this coefficient. So usually we say that, of course, this is imaginary. There is some ambiguity, but we should just say, take the real part. You just sum a bit, integrate above, integrate below. If you do it so, then, and compare to the numerical solution of the TBA, then you will see, because we are very precise. We calculated 7,000 digits, and we solved the TBA to 30 digits. We could see that this doesn't give back the physical answer. There is some exponentially small deviation between this real part and the numerical solution. So the question how to get that exponentially small pieces out of the asymptotic solution. And that we played a bit, this result. And to explain, probably most of you know this, maybe not all of you. I'm just introducing here the asymptotic analysis, how the asymptotic behavior of the perturbative coefficients is related to the analytical structure on the complex plane. Maybe it's useful for you. So let's assume we have a function and then it have a perturbative expansion with some coefficient which grow like factorial. Then you go to the Borel plane by dividing this factorial growth. And on the Borel plane, after dividing, I have some alternating part. And then there is a leading behavior, and there are correction, 1 over n times n minus 1 correction to the leading behavior. There is an alternating part, a non-alternating part, and then there are also higher terms, 2 to the minus n times, again, a constant, and the 1 over n, and so on. And so this is, from the analytical structure we have seen, we expect that this should be the behavior. And then what is nice thing, which is, I think, good to know if you have never seen such a resurgence, that you can actually resum all these guys. So from this asymptotical behavior, you can figure out what was the analytical structure on the Borel plane. And if you just sum up, say, the leading alternating part, then you will have a pole at minus 1. It's 1 over 1 plus t is this variable. But if you sum up the next guy, you will get a logarithm. So there is a log 1 plus t. And if you sum up these other guys, you will get an expansion of a function which multiplies this logarithmic cut. And you can do the same here on the other side. And then this, because of this 2 to the n, this will have a logarithm starting at 2. So now there is a very nice terminology, which is the alien derivative. So the function which multiplies this logarithmic cut, it's also asymptotic. So that what is denoted by the alien derivative of the previous function at the position minus 1 in this case, or plus 1 or plus 2 here. And the way to get this alien derivatives, you can just analyze the asymptotic behavior, and then you can describe. So these alien derivatives describe the jump, how your function jumps on the cuts. Okay, that's the alien derivative. So doing this analysis in our particular case, sorry. So here this psi bar, for example, which multiplies this logarithm, log 1 plus t, is the delta minus 1, yeah? And then here it would be delta plus 1, here it would be delta plus 2, and then that's the notation for the function which multiplies the logarithm. Later it will be very important, and I will show. Just on the next slide, I will explicitly show from these 2000 terms how we could fit these p numbers in the O4 model. So this is a generic slide. I think the one after will be also generic, but now let's see concretely if we really do the analysis. So what we did, So we just extracted the constant alternating piece, for example, using Richard Jones transform. And you got for many, many, many digits. And then there are even, yeah, recently we do it in Mathematica. You can ask Mathematica what is this number, sort of, if you have some ideas. But there are web pages, mathematician web pages, you just plug in and you ask what is this number. And then what it gives back, that it is like minus e over 8 pi for 150 digits. So this is this constant, and then you can extract all these numbers, yeah. So these are kind of the alien derivative, the perturbative expansion of the function which multiplies the logarithmic cut. So that you can extract so precisely. You can see this is really a pole. So all these other guys are 0 to that many digits. So it's like a numerical experiment. So you can calculate these alien derivatives at -1, 1, and 2 in our particular case. So the analytic structure, what you can see now, that there is this logarithmic cut starting at -1. There is only a single pole at 1. And there is also a logarithmic cut starting at 2. And then we cannot really see much higher, but this is what we can see now. But if this is the analytical structure of your function, then you can just make the Borel resummation in the sense that you integrate, make this lateral Borel integration a bit above. And then you see, you get, then you can do analytically once you know these alien derivatives, and you got exactly the same number we measured previously numerically. So we can explain why we got those numbers. So, but what about the real part? Yes. Say again. I mean, it's odd zetas, yeah, and then the transcendentality is always such that if you go to a given order, that every zetas, odd zetas up to that order can appear. This was obtained numerically just analyzing the asymptotic behavior of the functions, yes. This we extracted numerically for many digits, yeah. Mathematica can do it. If you know it's a zetas, then find integer null vector. It's a command in Mathematica, and you specify that it should be some zetas, and then it finds it, yeah. So now this is the explanation. If you, about alien derivatives, it's a very nice tool to calculate the jump of the functions. So there is some ambiguity in the result, and we wanted to understand this ambiguity. And of course, the ambiguity is related to these logarithmic cuts, because you integrate above or you integrate below, and the difference between the two will be exactly the function which multiplies the logarithms. So there is this notion that Stokes automorphism. So let's assume I take my function on the Borel plane and I integrate a bit above the real line, okay? And then if I integrate in below, then it's a different result, but you can ask the question, how shall I modify my function such a way that integrating above of the original function is the same like integrating below this modified function. This is called the Stokes automorphism, and this Stokes automorphism can be expressed uniquely in these alien derivatives. So this is basically the exponential of the alien derivatives. And what is relevant here, maybe picture-wise, so I have the logarithmic cut, the function multiplying the logarithmic cut, but that function also have a logarithmic cut. So you have to calculate the cut of the cut of the cut, and then these alien derivatives and the Stokes automorphism is exactly doing this. consistently to all orders. And then if we would like to understand this real ambiguity, what we found, this real deviation, we have to calculate actually the second alien derivative, because this is exactly where we got the deviation. And we have to calculate the asymptotics of the asymptotics. So this we did. So you calculate the asymptotical behavior here of these guys, and then we couldn't get in this analysis only like, I think 60 terms, but then you have to analyze the analytics, the asymptotics of that 60 terms, and then you could recover exactly those deviation, what we have seen. Time is running, so we could describe exactly those deviations. So when we analyzed the asymptotics of the asymptotics, and then we corrected the lateral Borel resummation with those terms, we could reproduce exactly the numerical result of the TBA. Yes, it was e to the minus 8. 8 alpha, 8 over alpha. Yeah, it was like this. So we could recover these terms from the asymptotics of the asymptotics, and this agreed with the numerical solution of the TBA up to that digits. So let me just summarize this game, what we played. So we had, the result, the exact analytical result, what we calculated kind of numerically, it must have this Tron series form. So we have a perturbative series that we have seen, and then we are trying to resum this on the Borel plane, this perturbative. But it must have also non-perturbative terms to compensate the ambiguity, and that can be extracted, this non-perturbative correction, from the asymptotics, large N asymptotics of the perturbative coefficient. And then analyzing the large N asymptotics, we could calculate in this Tron series form the leading and the next to leading terms. And by analyzing the asymptotic behavior of that guy, we could also calculate the first few terms from the large N asymptotics of the function multiplying that Tron series piece. We could calculate a few terms here. But of course, eventually we would like to see how many terms we have and then what those are. So for this, you have to solve actually the integral equation using the Wiener-Hopf technique. Before doing this, let me just mention a very similar analysis for that model I explained was the O4 model, but you can repeat the same for the O3 model. Just very quickly, the details is exactly doing the same analysis. The analytic structure is slightly different. We don't have a cut at -1. We have a pole at 1 and a cut starting at 2. And then we repeat. We analyze the asymptotics of the asymptotics. We expect that there should be a real deviation starting at e to the minus 8 over alpha. We compare to the numerics, and what we see that we have actually a much bigger real deviation already at the second, I mean the first Tron series order where we had the pole before, we had a full function which is there. From the numerics, we can extract these numbers, and this is not in the asymptotics of the perturbative series. It's something new. And because the O3 model is the only one which has instantons, we believe this should be related to the instanton action. So it would be very nice if somebody experienced with instantons and O3 model could actually find the instanton in a large magnetic field, calculate the action of the instanton, analyze small fluctuations, and then doing the calculation correctly should reproduce these numbers. So O3 model is different. Instead of solving this linear integral equation, and using the Wienerhoff technique, I would like to present now here just the solution, what comes out. So I'm explaining in the O4 model. The observable is this energy density, and with removing some trivial factors, it's called W11 here. There is the perturbative part, A11. And then once we solve the model, we know all these exponential pieces. And what we found, they can be expressed in terms of a basis of functions. These basis of functions are what we denoted A and M. Actually, these functions are the perturbative part of the generic observables O and M. These are very nice functions. We can calculate all of them any order we want. Numerically, 1000 order, analytically, 50 order. So we know this basis of function A and M perturbatively in the coupling. This V in the O4 model is 1 over 2B. In other models, this is a running coupling, which resums log B terms. So we can calculate this A and M to any order. It has these theta functions, and all trans-series terms, all non-perturbative corrections can be expressed in terms of these guys. So if we calculate them and then compare the previously fitted coefficient, we will see they are exactly the same. We got them by solving the model. And the generic form can be written here. And then let me just spell out a bit how you can interpret these terms. So you can think of this generic trans-series form, each term coming from a path on a lattice. So in this lattice, we have, say, the observable I'm analyzing, it's this 1, 1. This O11 was the energy density. The perturbative part is A11. So imagine a path starts from 1 and arrives at 1. So this very first piece can be just represented by, can be represented just a line coming here. And then the next order, we had this A1 minus 2 square times some Stokes constant. This can be represented as a path starting from 1, going to minus 2, and then from minus 2 back to 1. So that path describes the next piece in the trans-series. So this A comes, every line is a factor of A starting from 1 and minus 2, and then in this case squares. And then the next trans-series orders, I have two terms. I have the path going from 1 to minus 4, coming back from minus 4 to 1. And I also have 1 to minus 2, from minus 2, minus 2, and coming back to 1. So these two paths. And then to calculate the trans-series order, then you have to just sum up the index of the Stokes constants, and you will see at which order they will contribute. The location of this minus 2, minus 4, minus 6, it depends on the model. So I told you we are describing many models in the same time, principal chiral models, ON models. So this location where this index appears, it depends on the model. In the O4 model, these are every even integer where they appear. And then I already told you what are these A functions. And you can see the result is free of ambiguities because you can calculate the alien derivative of all these functions. And then maybe you are experienced in resurgence, but I've never seen such a structure. So this is a trans-series written in terms of these A guys. It's an infinite parameter trans-series. These A's, A and M's are the building blocks, and the alien derivative of this A and M is basically the product of two A's with this index in between, which is related to the alien derivative. The M, it's a special term. That was the pole term I told before. And they appear somehow because these two index of that object both are one, and then it's a singular limit. And then that somehow this extra small piece appeared in this singular limit. So here, for example, it's that number. It's it is written here. So it's integers. Yeah. I mean rational numbers. No zetas, nothing. No. So these are the Stokes constants here. Yeah. No, you have to calculate. We don't have it. So what I didn't mention, but you can derive some differential equation which relates different observables to each other. So if you know, say, O11, you can calculate O1M just solving these differential equations. And then how we got these numbers, we know from Wolin's method how to calculate A11, and then we just plug back to this differential equation and we could calculate all of them. But we don't have a closed expression. So one result which can be seen here in this full trans series, that they all higher order terms are generated by median resummation of the perturbative part. So all these higher terms are encoded in the asymptotics of A11. If you would know analytically the coefficient, then you could extract all these guys. So in this sense, this median resummation I didn't mention, but I mentioned the Stokes automorphism. Stokes automorphisms tell you if you integrate a bit above or below how you should transform your function such that they agree. So median resummation means that you integrate a but you use half of the square root of the Stokes automorphism, which basically would mean integrating on the real line. So that's median resummation. So the claim is that the median resummation of the perturbative part reproduces all higher non-perturbative corrections here. This is true for any ON models if N is not free. In the O-free model, what we found that there are free terms like a one instanton sector and a two instanton sector. So the full answer, the full observable, the energy density, is the median resummation of these free terms. So there was this A11, and there is an A1 minus 1, and an A minus 1 minus 1. And then if you sum up all these free terms, then you got the full answer in the O-free model. So in the language of paths, it means that we have the perturbative part, and then you have all the median resummation paths coming from this perturbative, these black guys, but you also have this A1 minus 1 extra piece, which is somehow there, and then it's not encoded in the perturbative. So you have this A1 minus 1 guy, and then all paths. These paths usually start from the first index and ends on the last index. This is the resummation. Logarithms. No, the logarithms are already resummed. So you can think of 1 over b's as the small parameters, and you have log b's. But we can always introduce a running coupling, like 2b equals 1 over v plus log v, such that when you rewrite the perturbative series in v, that all log v disappears. We can prove from the integral equation that you can indeed introduce such a running coupling, and we can figure out, of course, calculate how to introduce it. So even in this theory, this alien derivatives formula is still true, but in the O-free model, we have these free sectors. We have the perturbative sector, and then we have the first instance sector and the second instance sector. And this is true as far as we are in this running coupling based on the B. But if we go back to the physical free energy, then that running coupling actually contains the density. And on that physical Lagrangian-based perturbation theory, we have a new instanton sector at every order. This I haven't mentioned here, but this is true. What are these Stokes in the O3 case? Yeah, it's very similar. I don't remember by heart, but they are always related in the Wiener-Hopf. I can explain in general. So in the Wiener-Hopf solution, when you solve this problem, then you basically solve, maybe I have some slide, yeah. Yeah, I can explain a bit. So when you use this Wiener-Hopf solution, then you would like to solve this integral equation, where the integral originally was from minus b to b, but you can just instead extend this integral equation by introducing some unknown function, the integral of chi outside. And then that you can solve in Fourier space, but the price you have to pay, that you have some unknown function and you have to figure it out. The way you figure out that these unknown functions are defined actually between minus infinity to b, so its Fourier transform has a very specific analytic properties. So you have to project out some upper analytic or lower analytic pieces. So when you do Fourier transform, then you invert this 1 minus k kernel, and then you decompose like a piece analytic on the upper and lower half plane. And then you can transform projecting the appropriate components. I'm just checking if I have this function somewhere here. So you can project out these quantities. Yes, it's here. So, and the integral kernel, what appears is the ratio of this G minus and G plus. And in identifying where these non-perturbative corrections will come from, they come from exactly at the poles of that expression. And the residue of the ratio of this G minus G plus, these are the Stokes constants. So this is quite general and valid for any model, in particular for the O3 model it's also. And then here it's also shown what is the running coupling. So there is always a coupling which resembles log P here. You can see. So conclusions. So I explained you how we could use this nice algebraic relations to calculate many, many perturbative terms, and then we investigated the asymptotics of these perturbative terms, and we could extract the leading non-perturbative corrections. And then later, we could see that in the O4 model, the asymptotics contained all the information about the non-perturbative terms, but in the O3 model, they didn't contain. And then later, I didn't show but how to get it, but I showed that finally we can completely solve this problem. We can calculate all the trans-series terms in terms of these basic A and M functions. And then there is a very nice structure behind, which I never seen, but hopefully it will appear also in other places. Yeah, and then it would be nice if somebody could come and then figure out and do the instanton calculation and could reproduce the numbers we calculated from the integral equation. So thank you very much for your attention. Yeah. Maybe not I'm the right person to ask. Somehow the O3 model is small enough. I mean, topology. I guess you can argue by topologically, that you see the instanton should map the asymptotic infinity to the group, and then these other groups are just too big. You can unwind the instantons. Mhm. No, CPN is not integrable. Yeah, only classically. I think you can make an approximate instanton solution, but the phase space is bigger, and then it's not really a real saddle point. Just it's not really a minimum; it's a saddle point, I think. Yeah. Yeah. It should be classical. So yes. Yes. So the O3 model, it's expected to relate it to the instanton action. But here in other theories, you don't have instantons. So the belief is that they relate it to renormalons. What are the renormalons? So renormalons, they don't really have a semi-classical meaning. If you would do perturbation theory, then you would see that there are certain diagrams. So if you have instantons and you do perturbation theory, then your perturbative expansion grows because the number of Feynman diagrams, how you calculate, they grow. Okay, but if you have these renormalons, it means that there are certain diagrams whose individual contribution grow like factorial. And those diagrams are called renormalon diagrams. And it seems in these models, there are these renormalon diagrams. And then you have actually a good control in these diagrams in the large n limit. In the ON theories, you can play with this n. You can go to large n, you can solve at large n, you can calculate 1 over n corrections, and then you can even relate these non-perturbative terms I'm talking about with some specific renormalon diagrams. And this analysis was done by Marcos Marino and Ramon Miravitllas Mas and Thomas Strays. And maybe Marco Serona was also involved in some of the works. Serona, yeah. So you can read those papers, and then in the large n limit, they did a large n analysis, and then they made this mapping with exactly those non-perturbative terms I'm showing you in the O4. They exist for ONs, and then in the large n, I mean, no, they are not instantons. So I mean, non-perturbative terms are there, but those terms are related to renormalon diagrams. Yeah. So no classical, semi-classical interpretation of those guys, but you see they should be there. Yeah. Mm-hmm. 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 Mm-hmm, mm-hmm. 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 I see. Mm-hmm. Thank you. Is there a so so O4 model is actually like the SU2 principal chiral model. Yes. And then but these unitons are in finite volume, no? And then no. Mm-hmm. Yeah. Mm-hmm. But would it be possible to calculate actually uniton action and then fluctuations around uniton action? No, no. But it would be nice check. Yeah. Uh-huh, uh-huh. Yeah. Yes, yes. Yes, it is. Yeah, yeah, yeah. I mean, there is this paper of Marcos Marino. I mean, what you should do, you should in this Wienerhof, you can easily calculate G plus G minus, and then you can analyze the poles of or zeros of G plus, and you see the locations. And there was this paper of Marcos Marino when he actually compared some Renormalon prediction by Peneke and then other QCD persons, where they calculated maybe Parisi also, where they should appear. And then it seems in these integrable models they appear differently. In the large n limit they indeed appear there, but so it's model dependent, but you can calculate any of this model, the location of the non-perturbative terms, yes. Is a little, yes. So there is always this exponent when which appears in the in this index. So here is 1, 1, so that's why you have this e to the minus 2b. But if you would analyze like O alpha beta, then you would have e to the minus alpha times 2b, and also beta times 2b. It's symmetric in, these observables are symmetric in alpha beta, and you always have a non-perturbative term which is related to the index of that observable. So choosing this alpha very small, this can be actually very close to the origin, and it can be even leading ones. So they depend. It I just don't know if I have this. So for this generalized observable, you have some Wiener-Hopf equation with the source term, which depends on the observable. So this O n m observable, you solve the with n cos theta kernel, and then it explicitly appears as a pole. Yeah.